Assalamualaikum warahmatullahi wabarakatuh. Today, we would like to present to you satellite communication system. This slide is prepared by Nazril, me, ADNIN, TAQIUDDIN, HUKAIMI, ZARIF, and HAKIEM.
Okay, for introduction, a satellite is essentially a self-contained communication system that can receive signal from Earth and retransmit them using a transponder, a radio signal receiver, and transmitter that is integrated into the satellite. Satellite communication uses microwave radio frequency as the communication medium, with satellite bouncing and earthbound stations uplink signal back down to a receiving Earth station. A satellite communication system element consists of a ground-based Earth station (ES) to control the operation, a user network Earth station to provide the facility for transmission and also reception of communication traffic through the satellite station, a transponder, a radio repeater in the sky, and also the uplink and downlink that use different carrier frequency to avoid interference. And also it is important to note the frequency translation is done in transponder instead of the uplink and downlink. A satellite system link model essentially consists of three basic sections: an uplink, a satellite transponder, and a downlink. Further explanation will be explained by my group.
For our uplink and downlink model, the transmission of signal from Earth station to satellite through a channel is called the uplink. Similarly, the transmission of signal from satellite to second Earth station through a channel is called as downlink. For our uplink model, it uses intermediate frequency IF modulator, a band pass filter, up converter using a mixer, BPF, and uplink frequency microwave generator, a high power amplifier HPA, and a transmitting antenna TX. The signal which user wants to send is called as baseband signal. For our uplink model, the baseband signal will feed into the intermediate frequency modulator, which converts the baseband frequency to intermediate frequency through different types of modulation. And the output frequency from RF modulator will go through BPF bandpass filter, removing unnecessary frequency components. And the intermediate frequency will be sent to up converter, which increase the frequency megahertz to gigahertz, which is a radio frequency using a mixer and uplink frequency microwave generator. The radio frequency will go through another bandpass filter to make it more accurate. And lastly, the radio frequency will be sent through a high power amplifier to get enough power for long distance travel. And the radio frequency will be transmitted using a transmission TX antenna. As for our satellite transponder, it acts as a repeater as it consists of a receiver and a transmitter. The main function for our transponder is to pick up the transmitted signal from the transmission on the Earth, to amplify the signal, to translate the carrier frequency to another frequency, and to retransmit the amplified signal to the receiver on the Earth. Next. Our transponder consists of the following subsection: the receiving RX antenna, a bandpass filter BPF, a low noise amplifier LNA, frequency translator, a low power amplifier, and a transmitting antenna. The transponder implies to transmitter plus responder. The transmitted frequency from the uplink section and received frequency at the transponder via receiving antenna are the same. The noise filtering is performed by a bandpass filter, and then the radio frequency signal is sent to the low noise amplifier LNA, a tunnel node which amplifies the signal but keeps the noise level very low. And to get some specific advantage like small antenna size and less power consumption downlink frequency is usually kept 2 GHz less than uplink frequency. Our frequency translator performs the frequency conversion with the help of mixer and microwave shift oscillator. And again, the bandpass filter is used to get more accurate downlink frequency. And finally, the downlink frequency is passed through a low power amplifier LPA to gain enough power for long distance travel. And it would be transmitted through transponder transmission TX antenna.
So next is the downlink model. For downlink model, the signal from satellite transmitter we receive to the Earth, and the signal we receive by the Earth is called downlink. And the C-band frequency of downlink is 4 GHz. So as we can see here, the diagram is the typical of Earth station receiver. Next. From the previous diagram, the Earth station receiver is included by input baseband pass filter PPF, low noise amplifier LNA, and RF to IF down converter. The BPF function is to limit the input node to the LNA. It is because LNA is highly sensitive and is low noise device like a tunnel diode amplifier or parametric amplifier. And lastly, RF to IF down converter is a combination of mixer or baseband filter to convert the receiver RF signal to IF frequency. Next.
This is a satellite orbit or the movement of the satellite across the hemisphere. So the first satellite orbit is polar orbit. So it is the movement from north to south, and it is not usually used for telecommunication purposes. It is only used for weather and etc. So next is our elliptically inclined orbit. So this movement is only used in Russian domestic systems. Next is our circular equatorial orbit. So this orbit is only used in geosynchronous orbit or most of our telecommunication orbit, and it usually appears stationary or motionless when it is in space.
Okay, this is the slide for noise source. Okay, noise source is a source that we calculate in picowatts, which is the very small power to receive by the antenna. Okay, in the system noise, we have two main components to calculate the noise source, which is antenna noise and the amplifier noise temperature. Okay, and the next is the carrier to noise ratio, which is basically we have three formula to calculate the carrier to noise ratio because the small power is in picowatt. To calculate the noise power is PR minus PN and the result in dB, and CN equals to EIRP plus GR minus losses ESS minus K minus TS minus BN, which is K is the Boltzmann constant, TS is the noise temperature, and BN represent the noise bandwidth. Okay, what is losses? Losses is losses in noise source is the example of losses actually is sun noises, moon, earth, galactic noise, cosmic noise, sky noise, atmospheric noise, and man-made noise. Okay, carrier to noise ratio is GT. What is GT? GT is the receiver of the antenna. So when the diameter and frequency is getting higher, so the value of GT also higher. So next.
So this is some of the applications of the satellite. So it is used as a digital audio broadcasting to broadcast signals from Earth. And then next is our television distribution. It distributes some of the channels from Earth back to the satellite and being distributed to Earth. And next, it also serves remote areas where deep in the jungles, many of our cells can't reach there, so satellites can reach easily. It is also used in mobile communications.
As for the advantages and disadvantages, the advantages is it can access to wide geographical area, just like TAQIUDDIN explained just now. It is used for mobile and wireless communication application independent of location, so it doesn't matter where, but yeah, you still have the signal. It's covered wide area of the Earth, hence the entire country or region can be covered with just one satellite. And the second advantages is wide bandwidth. It provides wider bandwidth based on SCPC or MCPC allocation types. It coexists with terrestrial microwave line of sight communication. But this disadvantages is highly initial cost. Satellite manufacturing require more time. Moreover, satellite design and development require higher costs. The second one has propagation delay. Propagation delay is considered to be the time the signal takes to travel from the Earth transmitting station to the Earth receiving station, where the signal encounter an uplink and downlink way. That's right. As for the conclusion, in a relatively short span of time, satellite technology has developed from the experimental to the sophisticated and powerful. Mega constellation of thousands of satellites designed to bring internet access to anywhere on Earth are in development. Future communication satellite will have more onboard processing capabilities, more power, and larger aperture antennas that will enable satellites to handle more bandwidth. Further improvement in satellite propulsion and power system will increase their service life to 20 to 30 years from the current 10-15 years. In addition, other technical innovations such as low-cost reusable launch vehicle are in development, which increasing video, voice, and data traffic requiring large amount of bandwidth. There's no depth of emerging application that will drive demand for the satellite services in the years to come. The demand for more bandwidth, coupled with the continuing innovation and development of satellite technology, will ensure the long-term viability of the commercial satellite industry well into the 21st century. Next. So this is for our reference. That's all for us. Thank you.